the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. We now begin our wrap-up of graphing polynomials using end behaviors and zeros. So up to this point, you should have watched my videos on the zeros of polynomials and their multiplicities, and you should have also watched my video on end behavior of polynomials, because both of those are going to come into play right now. We're going to tie everything together and make a very nice ending to this entire section of material. So here we go. Graphing polynomials using end behavior and their zeros. So here we go. Theorem: if C is a zero of multiplicity K, we should know what that means. It just means that X minus C is a factor to the power K. Then the local behavior of the graph of the polynomial near C mimics that of y equals plus or minus x minus c to the k, where k is the multiplicity of the zero c. Now, there is a lot of density in that statement, and this is something that's not actually explicitly written as a theorem in most textbooks, mainly because it's probably a bear to prove, to be very honest with you. But let me just give you a few examples of what I mean by this. So let's pretend as though, and let me zoom in, because honestly that super far out doesn't work very well for me. Let's pretend as though we have a polynomial. I'll call it p sub 1 because I'm going to make another polynomial in a moment. And let's say this polynomial looks like the following: -3 times x plus 5 squared times x minus 1. Now, we already know how to state the degree of this polynomial. That's going to be very important. So the degree of p sub 1 of x is just going to be, well, let's see. I have a single degree on x from this factor, and then I have 2 powers of x from that first factor. So altogether, it is a third degree polynomial. That's pretty straightforward. Just add up the powers that would eventually be on x. You should not multiply that stuff out. I think I've mentioned that before. Just leave it like that. And then the next thing you're going to note is the end behavior. And the end behavior is going to mimic a master function. And that master function is going to be dependent upon the overall degree of the polynomial. If it's an odd degree polynomial, which this one is, it will mimic the behavior of x cubed with a slight modification. So I'm going to say roughly x cubed, but then I have to worry about the lead coefficient of the polynomial had I multiplied it out. So had you multiplied out this polynomial right here, you would be able to see that the lead coefficient is negative. It would actually be a -3x cubed, to be honest with you, but I don't really care about the 3. I just care about the fact that it is negative. So let's go ahead and write down the fact that it is roughly a -x cubed. And I mentioned it in the last video, but I don't really sit there and draw out x cubed. I also don't technically do this. Well, as x goes to infinity, y goes to -infinity, or whatever, right? I don't do anything like that. Instead, I just quickly sketch out what an upside down x cubed would look like. I don't even graph its middle behavior, even though I do know that if it were x cubed but upside down, it would look like that. But I don't really care to graph that out, honestly. I just want to know, what does this graph look like at the edges? And then we'll do the next step, which is the zeros and their multiplicities, for what that middle ground will actually look like. So again, let me repeat that. You find the degree of the polynomial, which in this case is 3, but what's more important is that it's odd, so that you can find out the basic behavior at the ends of the x-axis, so the end behavior is what we'd call that, but you still need to take into consideration the positivity or negativity of the lead coefficient. And this is a great reason why you should know transformations of functions. The negative in front of an x cubed means you're going to flip the regular x cubed function or reflect it about the x-axis. Anyhow, all right, so now let's go ahead and look at these zeros. And here's how I'm going to write this out. I'll write zeros, and then I'll make a little table here. Zeros versus their multiplicities. Now remember, the zeros for a polynomial are what you would plug in to make that polynomial turn into 0. So you can see easily that this guy right there requires that x equal -5 for it to be 0. So I know that a 0 is -5. If I plug -5 into my polynomial, it will become 0. And the multiplicity of that is just the power on that factor. And the other 0 is at 1. Again, it's from this guy right here. And its multiplicity is, well, 1. The multiplicities actually should add to the degree of the polynomial. That's kind of important to note. So let's go back to this theorem. The theorem says if -5 and 1 are zeros and they are multiplicity 2 and 1 respectively, then the local behavior of the graph near those zeros mimics x to the multiplicity power. It's actually x minus the 0 to the multiplicity power, but I'll mention that in more detail as we move forward. So let's go ahead and draw out an x-axis here and plot the zeros, -5 and +1. So I'll pretend as though this point right here is -5. I'll pretend as though this point is +1, which immediately tells me where the y-axis is. There's the y-axis right there. And I'll go ahead and write x here. All right. I also know that my function starts high and goes low. Well, that shouldn't be too bad. And now we can go ahead and use the multiplicity of those zeros to help us out. Now, again, this theorem tells me that the polynomial near x equals 5, -5, sorry. So near x equals -5, it's going to act like a plus or minus x minus a -5 raised to the multiplicity of that 0. In other words, it's going to act like the function y equals x plus 5 squared. And we know what that looks like. It looks like a parabola opening up. Well, it looks like a parabola. I'll just say that. The plus or minus is kind of important, but it looks like a parabola shifted to the left 5 units. The reason why I know it's opening up is because look at where it's supposed to end over here. So the only way for this function to go down here and strike against x equals -5 is if it opens up like a parabola. So that's the behavior right there. And now it'll climb for a ways and then it'll lazily come back down. And the next place where it'll hit the x-axis, it'll strike the x-axis like x minus that 0 raised to the multiplicity of that 0. Oh, and I should write plus or minus there as well. That is a line shifted 1 unit right. That's all it is. It's a diagonal line shifted 1 unit right. So it's going to look like this. I know it's going to go down because look where the graph is right now. There's no other x-intercept around. So it's not going to magically do this. Whoop. It's not going to do that because there's not an x-intercept right there. So I can't make an x-intercept. That's a huge mistake that students love to do. Don't create x-intercepts that aren't there. So it's just going to lazily go through here, and then it's going to go through this like a line, because that's what that exponent means. It's linear through there. And then it'll eventually match up with the end behavior and go down. And that is the actual graph of -3 times the quantity x plus 5 squared times the quantity x minus 1 to the first. Again, notice that at -5, it really does look, if you just look at it locally, like if I were to zoom into this window here, which I can't zoom in any further, unfortunately, but if I could, it does look like a parabola right there. And notice my note up here, right here, is that locally, it's going to look like y equals plus or minus x minus a negative 5, or x plus 5 squared, because that's the multiplicity of negative 5. So it's going to look like a parabola. The plus or minus, that's what I say here, on that equation is determined by the context of the graph. The fact that I started above this x-axis and the graph was falling here tells me that it's going to open up. It's going to just bounce right off there and open up. Now, a lot of people have heard about the bounce and cross stuff. And while I don't begrudge you for knowing that, in pre-calculus, you're going to learn a more rigorous way. I shouldn't say rigorous, actually. To be honest with you, it's just a better way of, a more accurate way of graphing. All right, so let's go ahead and maybe make up one more. You know what? I have examples. I should just use my examples. So here we are. Sketch a relatively accurate graph, including the zeros, the end behavior, and proper behavior near the zeros for the following function. Now, prerequisites, again, you need to know what zeros are. You need to know what a polynomial is. You need to know what the degree of the polynomial is. You need to know what the lead coefficient, how to compute whether the lead coefficient is positive or negative. But also, your instructor should have already gone through transformations of graphs. So you should know that, for an example, the graph x minus 1/2, this beast right here, that's a parabola shifted a half a unit to the right. You should know that. That's just something you should already know from your transformations work, functions. Also, something else that you should know is that whenever you have a power of, like, let's say that this wasn't a 2, but instead was a power of 12. Let's just pretend it was a power of 12. That the graph is going to look still very parabolic, except that it's going to be super duper flat. Now, if you didn't know that, that's actually from trigonometry. That's a trigonometry prereq. So if you're in pre-calculus, you've never seen that before, that's just the basic idea, that the higher the exponent, the flatter it is near to that 0 of 1/2. That being said, we pretty much have all the power in the world to graph this function pretty accurately. So let's go ahead and state the overall degree of this polynomial. If you look through the powers, and I should probably erase that 12 there. If you look through the powers, you have 3 powers of x there, 2 more, and 7 more. So that's a power of 12, actually. So the degree of this polynomial is 12. I think we've dealt with this specific polynomial in a previous lecture. So the degree of the polynomial is 12. And then if you think about the lead coefficient, the end behavior of this polynomial will mimic a x to the 12th power, but we still have to take into account the lead coefficient, the sign, not the actual value of it, but just the sign. Well, that's going to be positive. That's a positive. That's a negative. So therefore, the lead coefficient of x to the 12th, when everything is multiplied out, is negative. So this means that this polynomial, when graphed out, looks like an upside down parabola, right? Because remember that even polynomial powers always look like either parabolas or cubics. And so the end behavior here is going to mimic an upside down parabola, or a reflected parabola, if you like to say that. We still don't know the behavior in this middle ground. We have no clue what that looks like. But that's where the zeros and their multiplicities come into play. So I'm going to make a little table. Actually, I'll just make the table here. Zeros versus their multiplicities. And I'm just going to read this from left to right. And you're going to look at each factor and just ask yourself, what would turn that factor into 0? For example, that factor right there would turn into 0 at actually x equals 0. Its multiplicity is its power. The next one, what would turn that into 0? Well, 1/2. And its power is 2. And the last one, what would turn that into 0? Well, that would be a 1/3. This is one we'd done earlier. And its multiplicity is 7. We just didn't graph it. All right. All that being said, we are now actually ready to graph this polynomial. One thing I do want to mention before I forget is that you're rarely concerned about the y-intercept when you graph polynomials because powers can be very, very large. And so at the y-intercepts, they can be massive. Luckily here, the y-intercept is 0, but generally speaking with polynomials, it's very, very challenging to graph the y-intercept. All right, so let me plot the zeros. I have a 0 at literally 0. I have a 0 at 1/2 and 1/3. Now 1/2 is actually greater than 1/3. So I'll just plot that there, and here's 1/3. And I happen to know the end behavior is going to be down and down. Notice how I'm prepping everything with just plotting the points that are the zeros, and then also taking advantage of that end behavior. Now I'll start just like I would read a book from left to right. So I'll start on the left-hand side here. And generally speaking, when I graph something like a polynomial, there's a lot of kind of squiggly stuff going on here. So this is going to rise up, and near to x equals 0, it's going to look like x minus that 0 raised to the 3rd power. Or in other words, it's going to, well, and I should say plus or minus there. Or in other words, it's going to look like plus or minus x cubed. And if you take a look at this, because it's coming from below, it's going to look like a positive x cubed. So it's going to come up, it's going to swoop through just like an x cubed would. I'm trying to be somewhat accurate here. So it does something like that. Now, this is why I do a lot of scratch work here, like a little, you don't see me do a smooth curve when I graph this. Because then when I get to the next 0, which occurs at 1/3, it's going to want to, zeros are like magnets, it's going to want to draw it back down to that. So it's going to want to be drawn back down to that next 0 in line. But very important to note, that next 0, the graph is going to look like y equals plus or minus x minus 1/3 raised to its multiplicity, which is 7. That's a super high odd power. So it's going to look like cubic, but really flat, really, really flat. So I'll showcase that here. It's going to want to come down. Now remember, polynomials are smooth, so it's really hard when graphing by hand to capture this information, but it'll look like, notice how flat I'm trying to make that there. It's almost artistry, except I'm nowhere near an artist. But it'll look like a cubic going through there. Notice that does look very cubic going through there. Yes, I get it. It's very scratched. I totally understand that. But that's because I'm really trying to capture the flavor of this curve. All right. And now the next 0 occurs at 1/2. Remember, it's going to want to be drawn back to that 0 just like a magnet, right? Note 1/2 has multiplicity 2, so it's going to look like, locally, if I zoom in close enough, it's going to look like a plus or minus x minus 1/2 squared, like a parabola, shifted over 2 units, or sorry, half a unit to the right. So like a parabola, shifted a half a unit to the right is either right side up or upside down. The fact that my graph is approaching from below the x-axis, it's going to be upside down. But otherwise, it's going to look locally like a parabola. Now, I have to be honest with you. I can easily tell when somebody copies a graph from Desmos really easily because their graph is accurate. That sounds terrible, but even this graph is not super accurate. It has all the right flavor to it because it has that locally, this totally does in this box, totally does look like a parabola. And this one right here, locally, totally does look like x to the 7th power upside down. And right here, again, very locally, it does look like a cubic. Okay. But if you were to graph this in something like Desmos, you would find out very quickly that it is that your graph is not super accurate here. Often I'll see students that will draw a graph like this. They'll just basically have this, and I will give 0 points because that just tells me they are copying directly from Desmos. Desmos, actually, I will say our graph is probably much better than Desmos just because it really does showcase the values. You can't see it here very easily that it climbs up like a cubic. So let me go ahead and find an appropriate window to showcase this. Now it took a little bit, but I got it. So this is the same graph. You can see the cubic behavior at x equals 0. It does shoot off the screen. That's just because of the scale that I had to choose. And it comes back down and it does get really flat in there, right? Super duper flat. And then it crosses, comes down and comes back up like a parabola. In fact, if I were to zoom into that, it totally will look like a parabola. If I get close enough to it, you would say, if I just handed that to you, you'd say that's a parabola. So it is very cool, this idea of how graphing by hand that you can get the same exact behavior. In fact, I really like this one over here. I'm just going to zoom into this. If I just graph that, you would say that's a cubic, x cubed, but it's not. It's actually part of a bigger function. So that's us graphing by hand. A relatively accurate graph. And by the way, I should probably graph the y-axis on there just to really have a nice, clean, done graph. There we go. And yes, I expect my students to do all that work. To be honest with you, graphing polynomials is actually kind of not too bad. This type of question, I like this type of question for an exam because it really showcases your understanding rather than your ability to compute. It showcases your understanding. So what is the smallest possible degree that the polynomial whose graph is shown below can have? Well, let's just make up some numbers. Like this could be -5. That's probably -1. That's probably +1. And this is probably +3. And that's probably +5. Let's just say. All right. If that's the case, then the polynomial is at least, so I'm going to just say it's roughly x plus 5 because of that 0, x plus 1 because of that 0, x minus 1 because of that 0, and x minus 3 from that guy right there, and an x minus 5 from this guy right here. So I could easily count those up. 1, 2, 3, 4, 5 factors, and each of them have a power of 1. So I think that the degree of this polynomial, which I'll just call p, is at least 5. Could it be more? Maybe. It might be a higher degree. It depends. I can't zoom in enough to see if that acts like a line going through there. It sure does look like one to me. So that totally looks like an x minus a -5 to the first power. In other words, a line shifted 5 units to the left. It totally does look like that to me. So I'm pretty confident saying all of these are first degree locally, are like lines. Now, if it were an exam, I could be a little trickier, I suppose. I could say, what is the least degree that this could be? And I could modify it to look like that. And in that case, that root or that 0 at -5 looks to have, if you look at it locally, would look to have a multiplicity of 3. And in that case, I would say, oh, well, the minimum it would be is 3 plus 1 plus 1 plus 1 plus 1, or 4 plus 3, or 7. So it really does depend on the shape of the graph near those zeros. It's a really cool style of problem. I really dig it. Now, every once in a while, there's just a subsection of material that's so short, there's no use of me creating a separate video for it. And this topic here is a throwback to a previous section, which was titled Using Desmos to Graph. And I just want to bring it up because it comes up a lot in pre-calculus. My good students who are like my A and B students in pre-calculus often will ask, like, how do I find where that maximum occurs? Like, how would we do that? Do you want us to do that? For example, in this guy right here, I'll have students that say, do I have to find this value up here if I'm graphing by hand? And the answer is, in pre-calculus, heck no. You wouldn't find that high value, you wouldn't find that minimum value either. But in calculus, you'll be able to. In calculus, you can use what's called a derivative to find out when you have maximums and when you have minimums without using any type of technology. In fact, you can graph this perfectly in calculus by hand. So calculus gives us a lot of power. Unfortunately, it takes a while to get to that point. That power doesn't happen until you're about 80% of the way through Calc 1. Anyhow, that's what I'm saying here. Once done with previous material, many students just ask if there's a way to find the local max and local minimums, because that's what we did way back in section 2.2. And the answer to that is you'd have to use technology. It's the only way you could do it right now, unless you have calculus. All right, so that's the end of this lecture. I hope you guys enjoyed it as much as I did, and I hope everybody's safe. Have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.